Hello again. Okay, so today we got the light coming in the window here, giving this weird bubbly effect on the screen. As the sun moves, that will hopefully go away, or maybe not. Maybe you'll enjoy the bubbles, I don't know. Anyway, gonna sort of finish up the series I'm doing on metric versus imperial measurement systems. I could actually go into more stuff, but this is the last of the common things we're gonna cover. That's temperature. Now, one thing I like about the Fahrenheit scale, I'm going to come out and say right away, locally at least, it sort of runs the gamut of our what we see year to year. Um, 100 degrees is about as hot as it gets in the summer. It gets hotter sometimes. I think 106 is the highest I can remember. 0 degrees is about as low as it gets. And again, it gets colder than that from time to time, but 0 is a good average for low temperature locally. Globally, it doesn't work so well. And I got to wondering, is that where Fahrenheit actually set up his system? And apparently not. Although there is a German urban legend that he picked 0 because it was the coldest day of the year for when he set up his temperature, or his thermometer. Temperature scale, I should say. Problem with that is that he didn't just make a temperature scale, he revised it a few times over the year. Of course, we have Celsius going for the metric version of this. Except we don't have Celsius going for the metric version. We have Kelvin going for the metric version, although everyone will tell you it's Celsius. We're going to get into that a little later. But before we even do any of that, we got to go to the Romer scale. And I might be mispronouncing that. It is Ole Christensen Romer was a Danish scientist. Romer is spelled with an O with a slash through it, which is a Danish letter, and I've never seen how to actually pronounce that. I'm going with the Romer because I'm not sure how exactly to pronounce that letter. I don't even know how to look up how do you pronounce that. How do you look up O with a slash through it, or how do you pronounce O with a slash through it? Yeah, I don't know what kind of search to do to find that out. I guess I could go to someone who speaks Danish and ask them, but I don't know anyone who speaks Danish off the top of my head. Anyway, I'm getting off topic. So he created a scale. 0 was set for the freezing point of a brine solution. And why did he use a brine solution? And apparently there's something called euteric substances, and it's some weird euteric. I might be mispronouncing this because this is the first time I've ever heard about it. It's a homogeneous mixture where the freezing point is lower than the freezing point of any of its components individually, or something weird like that. And a lot of articles I found looking up, they made a big deal about, oh, he chose this system and it was important to him, and I don't see why. And I'm thinking more along the lines, I could be wrong here, but human body is mostly water and mineral, salt-like minerals. So he used brine, water, and an ammonium salt or ammonium chloride salt was the brine he used because it sort of mimicked human body chemistry. That's my guess. I could be wrong. I've never, that's it makes as much sense as this whole, well, he picked it because it's a special kind of, there are other euteric solutions out there. Why did he pick this one particularly? So I'm going to guess that he was actually going for something more similar to human body chemistry than any other reason. I could be wrong on that. But he created this scale. Now, Fahrenheit, he wrote to one of his friends when he was setting up his scale, and he told him basically, I took Romer's scale and I multiplied everything by 4. Because Romer was getting stuff where it's like, okay, this happens at 41.5 degrees, and this happens at 32.5 degrees, or whatever. And so Fahrenheit pretty much announced, I didn't like all these decimals, so I just multiplied everything by 4, and then I worked off of that. He did do other measurements, and he started off with let's do the brine solution is 0 and human body temperature is 96. And he picked 96 because 96 is divisible by a lot of things. And that's sort of where we get, like I've been discussing, everything else, the foot is divisible by many numbers, as opposed to the meter, which is only divisible by 2 and 5 and 10. So he was very big, apparently, on divisibility, which I like. Then later, he went with, okay, let's look at freezing point and boiling point of water. He revised his scale again. And he decided we're going to keep the freezing point at 32, because while our brine solution freezes at 0, pure water freezes at 32. So we're going to keep it there, and we're going to make the boiling point 212, because it's 180 degrees off from 32. And again, we can divide 180 by a bunch of different things easily. So that's why we got this weird scale for Fahrenheit. And everyone says it's random. Well, no, he actually put some thought into it, and it makes sense if you think about it, and it's very useful if you think about it. So that's how we did that, and then it was revised over time, because his measurements weren't 100% exact and stuff like that. But so things were adjusted on it. Anyway, it was, let's see, 1702 is when Romer came out with his. Oh, Romer, better known for studying the speed of light. And he actually came up with the first experiment to measure the speed of light. Or the first good experiment to measure the speed of light. And back in the early 1700s, his equipment wasn't that good, so he didn't measure it accurately, but he was in the ballpark because he had a good methodology. As for his work with the 1702 is when he invented the thermometer on the Romer scale, and he's not known for that at all. In fact, it wasn't, like I mentioned, there was this one letter that Fahrenheit wrote to a friend where he mentioned, I basically took Romer scale and multiplied it by 4. And then early in the early 1900s, someone found some paperwork by Romer where he discussed his method of measuring temperature. So Romer would have been completely forgotten if it weren't for those two items. Anyway, so we got that. Where's my date? 1740. No, that's 1742. I did not put the date on there. 1724 is when Daniel Fahrenheit sort of first published his, or that's when he's credited with doing it. Like I said, he played around with the system a while, but so he's credited with 1742 creating the Fahrenheit system. 1742, Anders Celsius comes along and says, let's do this differently. We're still going to use water, freezing point, boiling point, but we're just going to make it 100 degrees between them. Freezing is 0, boiling is 100. Now, one convenient thing about this is since Fahrenheit decided he'd use 180 as his difference, and Celsius decided he would use 100, it comes out to that a Celsius degree is 9/5 times the size of a Fahrenheit degree. And so, 9/5 is an easy number to work with. I mean, there could be a more convenient conversion scale, but still, 9/5, it's easy to memorize, not too hard to do the math with. The real problem is to convert it now, we have this difference between zero. Because one says water freezes at zero, the other says it freezes at 32 degrees. So we got to remember when to add 32 and when to subtract 32. And so that's the big problem with converting from Celsius to Fahrenheit, is remembering to add or subtract 32, depending on which direction you're going. Now, as I've said with everything else, water is as much a random substance as anything else. People want to say Fahrenheit, 32 degrees, that's just a random number for the freezing point, and 212 is a random number for the boiling point. And I've justified it. I told why he gave 32 for the freezing point and why he chose 180 degrees difference between them, and it makes perfect sense. For your day-to-day practical use, you want to be able to divide by many numbers and stuff like that. The use of water is random no matter what you do. Like I said, other planets where they don't use water as much, they might say, well, why did you use water for your temperature scale? It's random. So Celsius is as random as Fahrenheit in that sense of the meaning. And like I said, I like Fahrenheit because, again, throughout the course of the year, we generally run from 0 Fahrenheit to about 100 Fahrenheit. And yes, sometimes you go higher or lower than those numbers, but I can, look at the weather forecast and 96 degrees. Okay, well, I know this is about as hot as it normally gets. It sometimes gets a little hotter, but I know that I've survived this before because it's close to 100. So it's convenient to me in that respect. It's also convenient for stuff like cooking. Water boils at 100 degrees Celsius. That's interesting. It freezes at 0 degrees. Now, I worked at a place where they scientifically decided the best temperature for creating their pizza dough, or for fermenting it at or whatever. And so they calibrated their thermometers every morning to make sure we had the proper water temperature for making our pizza dough with. And to calibrate it, they basically put a thermometer in a glass of ice water and made sure that it read 0. So in that matter, the Celsius scale works good, except we could have just as easily looked at the thermometer and said, it reads 32. Other than that, like I said, 212 Fahrenheit is the boiling point. I don't know of any circumstance where I ever cooked anything at 212 or lower. I mean, boiling water, you put it on the stove, you just let it boil. You don't measure the temperature of it. You just let it boil. Other cooking, 350 degrees Fahrenheit, 400 degrees Fahrenheit, 450 degrees Fahrenheit. For cooking purposes, using Fahrenheit, you get these nice round numbers you can use, and it just works out better than Celsius. So again, day-to-day use, I like Fahrenheit better than Celsius. Anyway, so 1776 to 1777, the Royal Society, under the head of Henry Cavendish, one of my favorite scientists, revised the Fahrenheit system because England was still using Fahrenheit at the time. And basically, over time they had discovered a few minor glitches with what was going on, and their measurements were wrong. So we just adjusted things to better fit. So we're now doing the 32 freezing to 32 boiling point for water. We've got more accurate readings on this, so we're finalizing this. And so they were doing this while the army was off fighting the Revolutionary War, and so This is one good thing that came for the Brits in 1776, with that they got the temperature right. Just kidding. I like the British. Okay. 1848. William Thomson comes up with an interesting idea, and that is there's this thing called absolute zero. You cannot get any colder than this. So why don't we just make this a zero? And so he set up a system for this, and now his numbers were good. And yes, he discovered that, where is that? Like 273 degrees below, 273, negative 273 Celsius, let's say that, is the coldest anything can ever get. And he was off by 0.15 degrees, so that was pretty good. But some of his applications were off, and so a man named James Prescott Joule wrote a counter paper on this. Thomson's paper was on an absolute thermometric scale, and so the scale he was saying was bad, or the scale he was promoting was bad, but the actual numbers were good. And so James Prescott Joule comes back and he says, look, why don't we do it this way? Why don't we do it that way? So 1854, Thomson and Joule come out and they republish, and they come up with what's called the Kelvin scale, because Thomson later became known as Lord Kelvin. Interesting thing, so Kelvin scale is the actual SI or metric unit of temperature, not Celsius. Now, Kelvin uses the same size degree as Celsius. So, to convert from Celsius to Kelvin is just subtracting a number, or adding a number, depending on which way you're going. As opposed to, Fahrenheit to Kelvin, we have to add or subtract 32, then do this conversion, and then do another addition, subtraction, and whatever. So, that's convenient. It wasn't accepted as the SI unit or the SI scale until 1954. So 100 years after Kelvin discovers or finalizes, let's say, his SI unit, the rest of the world decides, we'll use this. Before we go into any more on that, I will also mention 1859, a man named Macquarn Rankine or something like that. He came up with his own system of measurement. Basically, it was, we're going to use absolute zero for zero, but instead of using Celsius degrees, we're going to use Fahrenheit degrees. So, zero is the same, and then 1 degree Rankine is actually, 9/5 larger than 1 degree Kelvin, or 5/9 larger. I didn't do that math in my head in advance. Anyway, so basically we're starting at the same point, and we're just adding Fahrenheit degrees to it instead of adding Celsius degrees to it. And now he was an engineer. He did stuff with steam engines, which were very popular at the time. So his theory was actually taken a little seriously, or his proposal was taken seriously, and it's actually sometimes, it's referenced more than Romer's scale, just because engineers were doing work with temperature, and so he came up with this scale based on absolute zero, but using the same size degree that was being used in the British Isles at the time. So they said, sure, why not? Let's try to use this scale for a while. And they eventually gave up on it, but it's still, you can still find references to it from time to time. And it wasn't lost like Romer's was. One more thing before we get off the subject of the British, when they switched to Celsius, I found an interesting note. Someone said that, so British Isles, they use Celsius now. But if they're having a heat wave, they'll occasionally give the temperature in Fahrenheit just to make it more sensational. Because again, 90 degrees Fahrenheit. Well, if you're thinking in terms of, if you're used to thinking in terms of Celsius, that's like close to boiling. But it's obviously not. It's far away from boiling in reality. So occasionally, British meteorologists will fall back on Fahrenheit just to make something sound more sensationalistic. I found that interesting. I've never been to England in the middle of summer, so I've never seen that happen. But it's believable. Anyway, so back to Kelvin. Interesting thing about this. So first off, Kelvin discovered absolute zero. So far, everything we discussed, distance and time and stuff, technically there's a 0 point, but it's sort of not measurable. I mean, you either have nothing or you have something. There is no saying this is the smallest possible length of distance, the smallest possible length of time, or, well, Planck times, but that's another subject altogether. Kelvin comes up and says, when we say there's nothing, we are actually talking about a specific measurement. It's zero. It's not just saying we have no temperature. It is saying, we can actually compare this temperature to other temperatures meaningfully. That's the first thing with Kelvin scale. Which, so I like it for that reason. Another interesting thing is doing science. When you are sciencing, as some people would like to put it, sometimes you're interested in change in temperature, and sometimes you're actually interested in temperature. And so, we're doing expansion of metals, and I'm building something and it's going to heat up, and that's going to cause the metal to expand, and so I got to figure out how much it's going to expand with the change in temperature. And doing that, since a Kelvin degree and a Celsius degree are the same thing, or the same size, it doesn't matter what you use. It's, change in temperature is, 100 degrees Kelvin to 110 degrees Kelvin is the same as saying 100 degrees Celsius to 110 degrees Celsius. 10 degrees, they're the same size, same amount of heat going into it. So that's useful. However, there are some times, like a few astronomy formulas and other things where you have to use Kelvin. And this is dealing with, not dealing with change in temperature, but dealing with absolute temperature. We have to know, the temperature is this, and we're going to plug that into our formula as opposed to a change in temperature. And so you have to remember to convert to Kelvin. And so I didn't go through, I could have gone through some of my old textbooks and some of my old science notes and found some examples of this. I didn't. But I just remembered there were a few times when you couldn't just use the Celsius. That was a trick that science teachers like to throw at their students was, I'm going to give them their measurement in Celsius and see if they remember to convert it to Kelvin. And so you had to. In order to get the right answer, you had to convert from Celsius to Kelvin, which some students forgot to do and got the wrong answer. So that's another thing is, everyone wants to talk about how Celsius is the metric unit. No, it's not. I mean, dealing with change in temperature, you can use Celsius. Dealing with absolute temperature, a scientist would want Kelvin for some problems. And so that's it. And this is pretty much going to be my last one on the metric versus imperial. I could go into things like force. There are actually imperial measurements of force, but we don't use them on a regular basis, and most of us don't measure force. Anyway, I sort of talked about weight when I did mass because that's sort of the, we sort of use those interchangeably day to day. Scientists wouldn't, but us laymen would. Electricity, we pretty much, when someone made a discovery or, named a unit of electricity, No one turned around later and said, well, here's a better system. Let's make this the metric version. We sort of stuck with the same measurements. Radiation, we have both a imperial and metric version. I might do that as a separate thing. Again, we don't. Most of us don't use radiation on a day-to-day basis. But we hear about it in movies a lot, so I might go into that on another as an independent video. And I might, as I've mentioned before, a lot of what we're calling metric and saying, well, it's not random. It's still based on Earth-based or human-based things, and I have brought up the question of how would an alien look at this. So I might do another video on that. Is and a universal measurement system, something based on you know what something we could take to an alien and say, look, this is how we measure temperature, and they'd say that makes perfect sense. And they wouldn't have to be familiar with humans or the Earth in order to understand our measurement system. Because we keep doing all this stuff. We want to talk to human or aliens, and we want to do this in a way they'll understand us. And no one ever thinks of our basic units. We think about the math, and okay, should we use binary? Should we use base 10? No one ever thinks, if we talk about distance, how should we measure distances? The light year. Okay, speed of light's basic, but the year is Earth-centric. If you're not familiar with Earth, you won't know what a light year is because you don't know what a year is. So I might do a video on a universal measurement system. What could we use if we wanted to communicate with aliens who knew nothing about us? That's going to be very sloppily done because it's going to take a lot of research, which I don't have time to do. It's going to be more of a theoretical talk. But this, like I said, this is going to be my last official one on metric versus imperial. I might do, like I said, radiation. I might look at later, but it's going to be sort of just its own standalone video. I'm sort of dragging out time here talking about this, so I'm going to just end now. Have a nice day.